All right, let's just dive right in. We're using the title from the source paper for this explainer because, let's be real, it's the question we're all asking. The term AGI, artificial general intelligence, is absolutely everywhere. But what does it actually mean?
You know, Michael Bennett, the author of the paper we're looking at, just nails it with this quote. AGI has become a total Rorschach test. For some people, it's Skynet, just waiting around the corner. For others, it's just a meaningless buzzword. You see whatever you want to see. So, what we're going to do here is try to cut through all that noise and get to a solid, useful foundation.
So to get that clarity, we have to start with the big one. We need to redefine intelligence itself. We have to get past all the hype and land on a definition we can actually build on. Now you hear this phrase, human-level performance, thrown around all the time, right? And it sounds good, but it's super vague. The paper gives us something way better, way more concrete. Intelligence is just adaptation with limited resources. How well can a system deal with new problems, given the time, the data, and the energy it has? Now that is a much more useful way to think about it.
And this leads us to a really brilliant analogy for AGI, the artificial scientist. If intelligence is all about adapting, then a true AGI is a system that can adapt like a human scientist. Think about it. It can come up with ideas, figure out how to test them, and then actually learn from the results. It has a purpose, a drive to figure things out.
Okay, so if that's our goal, to build an artificial scientist, what are the building blocks? Well, according to the paper, every intelligent system is built from just two fundamental tools.
On one side of the coin, you've got search. This is your logic, your planning. It's super precise. You can verify the answer. When Google Maps finds you the best route, that's a search algorithm at work. On the other side, you've got approximation. And this is pretty much all of modern machine learning. It's amazing for messy, real-world stuff like picking a face out of a crowd. It scales like crazy, but it's imprecise. It's a good guess, not a guarantee.
And what's so cool here is how they're basically opposites, with totally different strengths and weaknesses. Search is great because you know it's correct and you can understand how it got there. But man, is it slow and expensive. Approximation? Super fast, great with messy data, but it's often a black box. And by its very nature, it's just a guess. It's not the actual ground truth.
So, here's the secret sauce. The most powerful systems are hybrids. The perfect example is AlphaGo. It didn't just use one giant neural network. No way. It combined the logical power of search to explore all the possible moves with the intuition of approximation to guess which of those moves look the most promising. That combination is how it beat the best player in the world.
All right, so let's go one level deeper. We've got our tools, search and approximation. How do we actually use them? The paper lays out three competing philosophies. Think of them as big bets on the best way to build our artificial scientist.
The first one is going to sound super familiar because it's the one that's been dominating everything lately, scale-maxing. This whole idea comes from Richard Sutton's famous bitter lesson, which basically says, forget your clever little algorithms. In the long run, brute force always wins. Just add more compute, more data, and make the model bigger. And I love the name the paper gives this era, the embiggening. The examples are just wild. GPT-3 was trained on 45 terabytes of text. AlphaFold 2 tackled the 50-year-old challenge of protein folding by, and I'm quoting here, throwing an entire data center at it. That's scale-maxing for you.
But here's the catch, and it's a huge one. We are hitting a wall of diminishing returns. You see it right here. We're cranking up the model size. We're burning through insane amounts of compute. And the actual performance gain we get back, it's getting tinier and tinier. It's just not sustainable.
Which leads us straight into philosophy number 2, simp-maxing. And it is the complete opposite. Instead of bigger is better, the mantra here is simpler is better. The core idea is that the simplest model is the one that's actually going to understand the world and make the best predictions. And the guiding light here is a classic you've probably heard of, Occam's razor. The simplest explanation is usually the best one. For AI research, this gets translated into a really powerful concept. Intelligence is compression. The smartest model is the one that can compress the data the most, the one that finds the simple, elegant pattern instead of just memorizing all the noise.
And finally, we get to the third and, honestly, the most radical idea of the bunch, we-maxing. Now this one's a little more abstract, but stick with me, because it's incredibly powerful. It's not about how big the model is, or even how simple it is. It's about how flexible its function is. The idea is that the most adaptable, most intelligent systems are the ones that use the weakest, most general rules possible. So what does that actually look like? Well, the playbook for mind-maxing looks a lot like biology. First, you weaken the constraints. You don't hard-code every little detail. Second, you delegate control. You let smaller parts of the system self-organize instead of having one central brain micromanage everything. And third, you unify mind and body. You stop thinking of software and hardware as separate things. They co-evolve as one system.
And if you're thinking, okay, that sounds kind of out there, well, check this out. The paper points to experiments where applying this maxing philosophy led to a 110 to 500% improvement in generalization over just trying to make things simple. I mean, that's not just a small improvement. That's a whole different ballgame.
So we have these three competing ideas: scale, simplicity, and this wild, flexible approach. Where does that leave us? Well, the paper's big conclusion is that the future isn't about picking a winner. It's about a fusion.
This table just lays it all out perfectly. You've got scale maxing, running on brute force, but it's super inefficient. You've got simp-maxing, which is great at generalizing, but can kind of ignore the physical world. And you have W-maxing, which is incredibly adaptable, but yeah, it's conceptually really hard to wrap your head around. Each one holds a critical piece of the puzzle.
And here it is, the core argument of the whole paper. The embiggening worked because our biggest problem was just a lack of hardware. We threw more GPUs at it and got amazing results. But that era is ending. The new bottlenecks, the really hard problems we have to solve now, are learning from less data, that's sample efficiency, and using less power. And pure scaling is terrible at both of those.
So the path forward is becoming pretty clear. Scale still matters, of course, but it's not enough on its own. It has to be fused with the elegance of simp-maxing and the wild adaptability of wa-maxing. We're already seeing this happen in newer models. And when you think about the next frontier, truly autonomous agents, you're absolutely going to need all three of these philosophies working together to create systems that are genuinely intelligent.
Which leaves us with this one last huge thought. The brute force embiggening gave us chatbots. And don't get me wrong, that's incredible. But what happens when we really master this fusion? What kind of artificial scientist emerges from a system that combines massive scale, elegant simplicity, and biological style adaptability? That's the question that is going to define the next decade of AI, and probably a lot more.